In previous lessons, I've given you an overview of both infrared and UV-Vis spectroscopy, and we're going to review those again today. Before we review those forms of spectroscopy, we need to talk about mass spectrometry. A mass spectrometer is very different than any type of spectroscopy because spectroscopy involves the interplay of photons with molecules. Spectrometry is something else. And mass spectrometry operates based on fracturing your molecule and then looking at those broken fragments to determine what the molecule used to be. This diagram down here represents the internal workings of a mass spectrometer. So if you walked in the laboratory, all of this would be housed inside of a large box, and they're typically several feet wide by several feet deep by several feet tall. These things tend to be fairly large. At least this particular version tends to be fairly large. This is now kind of an outdated diagram, but the principles are still correct even though they've updated the instrumentation. We can think about the process of mass spectrometry in 4 different steps, indicated here in red and then written out here in your lesson, and we need to define each of these steps. The first step is ionization. Your sample, typically in a relatively pure sample, is injected into the insert port of the mass spectrometer, and then ions are created. Now, this process of ionization involves a high energy electron smashing into your substance that you're analyzing. The substance that you're analyzing is called the analyte. So a high energy electron plows into your analyte, and during that collision, that original electron just keeps going right through the molecule. Just imagine it just kind of tearing through the molecule, and in that process, it bumps off an additional electron. This means that the process of ionization involves firing a high energy electron at your substance. That electron again passes through it, but tears off a second electron, so your analyte will always take on a positive 1 charge. Now, that isn't the case in all forms of mass spectrometry, because occasionally you'll end up with a case where they end up with different charges. But in all of the examples that we're going to evaluate, this is the model, and they will take on that positive 1 charge. The second step after ionization is acceleration. These newly formed positively charged cations are attracted to negative charges that would be located at this position, and the attraction between the positive charges and the negative charges kind of whips these things down the tube. Once they're sent accelerating down the tube, then they are deflected by an electromagnet. So there is always an interplay between charged particles and magnetic fields, and a stronger electromagnet will deflect the particle more sharply. And so you can tune the instrument so that the heavier particles make kind of a wider turn, and the smaller particles with less momentum make a sharper turn, and the particles that you're interested in analyzing at that particular moment are the ones that exactly make it down to the final step where they trigger a detector. So deflection and detection is how these ions that are created are sorted, separated, and registered by the instrument. So in summary, a sample is inserted into the instrument, it's ionized, that cation is accelerated down the instrument tube, it is deflected based on its mass, and then ultimately registered by a detector. Let's consider what happens when one particular molecule goes through this process. And we're going to look at 1-propanol. So here's a molecule of 1-propanol. This is a liquid at room temperature. And so you would maybe synthesize this liquid in the laboratory, you'd purify it, and then you would inject a very small quantity of it, maybe like 1 microliter, into the mass spec. That's what they call it for short. And inside of the mass spec, what happens is a single electron is fired into this. So they'll typically refer to this as plus an electron. This means an electron is being fired at this substance. And in that process, that electron, again, comes in with high energy and smacks into the compound, rolls through it so that it comes off of it. So we also have minus an electron. But during that process, it also takes another electron with it. And so it's not just one electron, so it is one electron coming in, but it's actually two electrons that exit the system. So this is kind of a common shorthand that you'll see when people are showing the first step of mass spectrometry, that one electron comes in and two electrons leave. And the electron that comes off typically comes off of the weakest or most susceptible electrons. And that generally occurs with lone pairs. So if you have a lone pair of electrons, that means only one atom is actually holding on to those electrons. And so it's easier to bump those electrons off because they're only being held by one atom. That statement's not entirely true, but it works well enough. And it's not just a radical that I've given this compound. When I hit it with that one electron and then a second electron follows that first electron out, it ends up forming both a cation and a radical. And sometimes they just refer to this as the molecular ion. The molecular ion is the entire molecule that we started with as just an ion. And in terms of mass, the mass of an electron is so small compared to the the mass of a proton or a nucleus or anything else, that losing an electron does not cause you to undergo a significant loss of mass. Structure. Okay, yeah, here it shows you. This right here is an accurate an exact mass of 60.06. That's how much this compound weighs, 1 propanol. If now I just look at this compound, it still weighs 60.06. So out to the tenths hundredths place, the mass is not going to change due to the loss of a single electron. This electron that is fired at the compound is given much more energy than is needed to simply carry a second electron off. I think they estimate that it's usually given about 7 times as much energy as is needed for a simple ionization event. And the rest of that energy is given to the molecule, and it causes the molecule to start to vibrate wildly. So not only is this thing now a cation, the positive charge, while simultaneously also being a radical, it's also highly energized, and this causes the compound to start to decompose. It actually breaks. And so this is, earlier I said that in mass spectrometry, what we do is we shatter the compound and then we evaluate the pieces that come off. So some percentage of all of the molecules that I put inside of my instrument, inside of the mass spec, are going to undergo a single ionization event, which is what's shown here, and then they'll make it through to the detector without undergoing any more decomposition. An alternate occurrence is when they undergo decomposition. So we're going to look at 2 different common decomposition events. The first decomposition event is when the heteroatom, remember a heteroatom is not a carbon or a hydrogen, the heteroatom is typically the one that takes on the positive charge, where it simply takes its electrons away from the neighboring carbon and falls off, and just does that. So this arrow that I'm showing right here would produce as fragmentation pieces this resulting compound. So I'm going to take this same structure, and if I take those 2 electrons right there, unmake the bond, and give those 2 electrons to this oxygen right there, then that oxygen no longer has a positive charge. So this is referred to as the hydroxyl radical. Clean that up just a tad. I think I liked it flipped around the other way. Okay, so when I disconnect the hydroxyl radical right here, I just took 2 electrons away from it, gave it to the oxygen. The oxygen now no longer carries a positive charge. This is a neutral radical. And because it doesn't carry a positive charge, this compound right here will not trigger the detector. So when I detect the ions that have made it through to the end of my instrument, this is not an ion, and the instrument will not detect this particular fragment. What it will detect instead is the other fragment. If I take that bond and pull it off of the carbon and give it entirely to the oxygen, then I end up making a carbocation. And you might ask, hopefully, wait, that's a primary carbocation. I thought we were never supposed to see those. And the answer is sort of. If you're building a compound, you should never go through a primary carbocation intermediate. When you are shattering a compound, you're going to see some weird things, including primary carbocations. This is not stable. It just needs to last long enough for this molecule to run into the detector. The original mass of this particular starting material was 60. It was 60. So let me make sure. There are 3 carbons. So the molecular formula is C3, 1, 2, 3, 4, 5, 6, 7, H8O. This was the original molecular formula. And C3H8O has a combined molar mass of, well, there are 3 carbons. Each carbon weighs 12. So 3 times 12. Plus there are 8 hydrogens. Each hydrogen weighs 1. And there is 1 oxygen that weighs 16. So 3 times 12 is 36. 8 times 1 is just 8. And then 16. So if we add these two together right there, this is 24. And 36 and 24 is 60. So the molecular mass of this original 1-propanol was 60 grams per mole, or sometimes referred to as 60 AMUs. This molecular ion over here is going to have a mass of 60 as well. I tried to make the argument before that losing an electron does not substantially change your mass. The way they will typically write this is that the mass is equal to 60 AMU. And because not every single mass spectrometer generates only positive 1 charges, they do like to specify the charge as a ratio. So you're going to see this term M over Z. And because we're only going to look at examples that produce a net positive 1 charge, that means that Z, the charge, will always be positive 1. And if you divide anything by positive 1, it doesn't change the value. So to us, M over Z is just simply the resulting molar mass. But to organic chemists, M over Z is the molar mass divided by the net positive charge that the molecule has taken on. And so if you had a positive 2 charge, which we won't show you in this class simply because we're not going to evaluate those kinds of examples, then you need to know what the mass to charge ratio is. So it may seem tedious to constantly refer to this as M over Z, but it is relevant in other experimental setups for us to try to keep track of different charges that could exist during this ionization event. And we're only going to ever see a positive 1 charge. Okay, now the reason I said that is the mass to charge now of this compound is going to be 60 minus however much we just broke off. So if you break off an oxygen, then that weighs 16. And if you break off a hydrogen, that weighs 1. 16 plus 1 is 17. So the molar mass of this piece right here is 17. They don't typically worry about the molar masses of the pieces that don't hit the detector, because this hydroxyl radical that has a molar mass of 17 AMU does not carry a net positive charge, so it doesn't really hit the detector. So they typically don't bother to label it. The reason that I'm keeping track of the mass is if this weighed 17 and the parent weighed 60, then that means that the other fragment must weigh 43. 16 minus 17 is 43. And it has a charge of plus 1, so the M over Z ratio on this one is 43. And when they report this as a ratio, it is common practice for them to no longer report the units. So they'll just say M over Z 60 and M over Z of 43. This particular degradation pathway, where the heteroatom just simply takes its electrons and falls off, is pretty common. Let's see what that looks like now with the data that is produced. So this right here is the typical readout that the mass spec instrument would give you at the end of sending 1-propanol through the instrument. On the x-axis, I have that M over Z value, mass per charge. Since our charges are always going to be plus 1, this is basically just an axis that shows you the molar mass of the different fragments that make it through and strike the detector. And you should realize pretty quickly that the most common fragment that's hitting the detector is the tallest peak right here. The detector counts every ion that strikes it, and based on the power of the magnet, and you have to pre-calibrate this to know, but essentially the detector counts each of these ions and assigns them an m over z value, and then produces a graph where the taller the graph is a higher count. So if you think about this in terms of pixels, maybe for every 1,000 ions that strike the detector, it adds 1 pixel to this particular line right here. So we don't care how many individual ions strike the detector at each mass. We just want to point out that the most common fragment that's striking the detector has a molar mass of 31, or a mass to charge ratio of 31. And those molecular ions, those peaks that represent a single electron loss where the molecule then undergoes no additional degradation, that's what would have to happen for a piece of the compound to make it all the way through to the detector that weighed 60, that's not a very common event. Now notice how short that peak is. That tells us that very few of the 1-propanol are actually making it all the way through the detection apparatus without undergoing some type of decomposition. And also that peak that we predicted, well, that I predicted at 43, there's really not a lot of those. This is 41, 42, 43. Very few of the molecules are actually making it through to the detector with a mass to charge ratio of 43. So if 31 is the most common peak to hit the detector, then mechanistically, what would explain that? Well, I told you that there are different degradation pathways that are common. There's 2 that we're going to primarily focus on. Here in the black arrow, I showed you the simplest possible degradation pathway. The heteroatom, offended by the loss of its electron, simply takes its bond and goes home, like an angry kid taking his basketball and going home. The other pathway is more cooperative, and in this particular case, more common. What it does is, instead of taking this bond and leaving, forcing the carbon to adopt an unstable primary carbocation, I'm going to draw this molecule again and show you that alternate pathway, not with overlapping arrows, but somewhere else entirely. So what we'll do, is we'll consider that the molecule can go 2 different directions, but in both cases, it's the same first step. Okay? The 1-propanol will get ionized by the ion cannon and then loses a pair of electrons, and we get to this cation radical. Instead of the oxygen simply taking its electrons and leaving, what it does is doubles down. Okay? And by that, I mean it takes this remaining electron and offers it to this carbon right here as a pi bond. So I'm going to draw more detail of this carbon so you can kind of evaluate the choices that this carbon right here is going to make. When it does this, when it takes this radical and offers it to the carbon as a pi bond, think about it like shaking its hand. It offers a hand of friendship here, and the carbon has to choose to give up one of its attached atoms. And we're going to give up this carbon over here on the left-hand side. What it does is it takes this bond between these 2 carbons right here and just breaks it. And half of the bond goes in to meet this oxygen electron to form a pi bond, and the other half falls out onto this carbon to form a radical. The products of this particular step are going to look like this. We're going to end up with an ethyl radical right here. And this is not a highly stable compound. So ethyl radicals are better than primary carbocations, but not great in and of themselves. It doesn't like giving me a single line here, but that's just a ChemDraw style issue. The rest of the compound looks like this. Because that carbon and that oxygen collectively agreed, each of them, to donate an electron into the system, they will end up forming a pi bond, a double bond between them. These 2 hydrogens are still there on that carbon, and the oxygen has a lone pair but it also still has that original hydrogen it's connected there. This results in a product that carries a net positive charge. And so this is what's going to activate the detector. This radical right here doesn't have a positive charge, so it's not going to do anything substantial to the detector. It's this structure right here. This ion is what the detector will pick up and start counting. And the mass of this particular ion, its chemical formula is C, and there's one carbon, there's 3 hydrogens, and 1 oxygen. Okay? So a carbon weighs 12. 3 hydrogens weighing 1 each will add 3, and the oxygen weighs 16. So the combined molar mass of all of this is 15 and 16 is 31. And if you go back to the spectrum right here, notice how there is this massive peak at 31. This means that as one propanol is going through your sampling tube, and this happens within just fractions of a second, it gets ionized and immediately starts to decompose. A few of the 1-propanols will make it all the way through to the detector without any decomposition. That's what's going on right here at 60. But the majority of them are undergoing this decomposition event that produces a peak that has a molar mass of 31. And the molar mass of 31 occurs via the 3 half-headed arrow pathway. So we're going to commonly see 2 pathways. The take your electrons and leave pathway that just involves 1 double-headed arrow, or the kind of doubling down effect where you offer 3 half-headed arrows and you split off something that's connected to this carbon right here. And this particular pathway is more likely based on the data. It's what we refer to as the highest intensity peak. So they refer to relative intensity. Whichever peak is the highest, they just assign a value of 100. And then every other peak is scaled according to that. So this particular peak right here is the highest peak, sets the parameters of the y-axis. So your highest peak will always be given a value of 100, and everybody else is some percentage of that peak. So it looks like this peak at 60 is right around 17 or so, and that means that 17% of the height of the tallest peak is reflected in this peak at 60. Now, it would be a nightmare if we had to go in and justify every single one of these individual peaks. So we won't. What we'll typically look at is the molecular ion peak. That gives you the molar mass of the whole compound. And then you evaluate the 2 common degradation pathways. We're going to look at a few more examples and focus on these 2 different degradation pathways. It should make sense that this pathway that produced a compound with an M over Z of 31 is a better pathway, and the data tells us that it's definitely more probable. That's why this peak is higher, that more often than not, the molecule is undergoing this 3 half-headed arrow mechanism. And the reason for that is the other pathway is producing a primary carbocation. That is an unlikely pathway because of how unstable primary carbocations are. Whereas this pathway still produces the primary, but now it's a radical instead of a carbocation. Primary radicals are still not stable, but they are definitely more stable than primary carbocations. So you can make arguments of stability using the same considerations we've been thinking about all semester long to try to predict which degradation pathway is more common. It is worth looking at a couple of peaks specifically. You'll notice them listed out here. We explained the peak at 60. This is the molecular ion peak, and this just represents a single ionization event. The peak at 31 is a carbonyl fragment. Remember, a carbonyl is a carbon-oxygen double bond, and so this carbonyl fragment is this one right here. In fact, I should incorporate in my answer, I should probably try to leave the mechanisms here. That's actually the best way to explain all of this. So I'm just going to dump those mechanisms right here as my explanation. The carbonyl fragment, which is the most stable degradation pathway that avoids the primary carbocation. the peak at 43, which is this one right here, and I'll put a little note here that this is the 3 half-headed arrow mechanism. The peak at 43 is a primary carbocation, and formed by the heteroatom taking its electrons and leaving. So these two mechanistic pathways, the 3 half-headed arrow pathway and the heteroatom taking its electrons and leaving, are the two pathways that you're going to encounter most commonly. Let's try to figure out what's going on with these other three peaks, this one at 61, 59, and 42. I'm going to start with the 59 and then go to the 61 and then come back to the 42. So let's think about the 59. And we can actually do that in the context of this mechanism right here. If your molecular ion weighs 60, and I'm asking you, how would you get something that weighs 59? The answer is, well, it loses a hydrogen. And the simple hydrogen to lose would be this one right here, but that's not what happens. The oxygen doesn't just reach over and pull the electrons off of that hydrogen, because if it did that, the hydrogen would end up with the positive charge and the resulting fragment would not. So let me show you what that would look like with an arrow. If the oxygen simply takes its electrons away from the hydrogen right there, we'll call this pathway blue, the resulting fragments out of that pathway would look like this. And then we're going to take this thing right here, we'll redraw it over here. The positive charge moves over onto the hydrogen, and this ends up with a lone pair like that. That particular pathway, it might happen, but the problem with this pathway is, remember, the detector picks up things that carry positive charges. And so the only thing here with a positive charge is a single hydrogen atom, which would have an m over z of 1. Let's go back to the data and see, and the chart doesn't even go down that low. So if this pathway is happening, we wouldn't detect it because the positive charge is the thing the detector registers, and its mass would only be positive 1, and we can't see positive 1 on our particular scale. So this is not where we're finding that peak at 59. But this right here would weigh 59. Unfortunately, though, it wouldn't have a positive charge, so the detector wouldn't register. Instead, what happens is an alternate variation of the 3 half-headed arrow mechanism. If you remember, in the 3 half-headed arrow mechanism, let's see, I'm going to draw this right on top of this other one, and we'll do it in a different colored arrow. The 3 half-headed arrow mechanism, the oxygen offers up one of its electrons into a pi bond. The carbon matches that offering by taking an electron away from one of its bonds. We already looked at the consequence of it taking it from the carbon-carbon bond, but what if instead it takes it from this carbon-hydrogen bond? That would cut the hydrogen free as a single unit right there, and this would end up producing a mixture of compounds that look like this. I grab this, and the bond that we broke right here was this carbon-hydrogen bond right there. This free radical ends up bonding to that hydrogen instead, and so we'll change that. It looks like it already did, it's just not registering it in the graphics. There we go. And then this oxygen and this carbon now have a double bond. So let me color this whole pathway different colors so that you're not confused about overlapping structures. We'll make this pathway red. So there are always going to be multiple different variations of the 3 half-headed arrow pathway. It just depends on this carbon, the one that's adjacent to the heteroatom, and what it decides to give up. So what we're finding here is that the most probable pathway was this pathway that produced the peak at 31. And we know that it's most probable because that was the tallest peak in the mass spec, meaning that this is what happens more often than anything else. The second most probable pathway is the next highest peak at 59. And this compound right here would have a molar mass of 59. So we want that analysis window again. And the analysis window does the math for us and tells us that the molecular weight of this fragment is 59.09, which is close enough to 59 that that's what we're going to call it. So I'm going to go ahead and finish up with the labeling. M over Z equals 31 was what we had for this piece right here. This piece had an M over Z of 59. Okay, and so that explains now the 60. We've got the 43, the 59, the 31. The next thing I want to talk about is, what about 61? Well, let's go back to this molecular ion peak right here. And what you'll notice is that the molecular weight is 60.10. Carbon's supposed to weigh 12. Hydrogen's supposed to weigh 1, and oxygen's supposed to weigh 16. So how can that all add up to give you something that has a mass of 61? And the answer is isotopes. For every so many carbon atoms in the universe, some number of those, the majority of the carbon atoms, at least in our solar system, are carbon 12s. But some of the carbons are going to be carbon 13s. And for hydrogen, most hydrogens have just a proton in the nucleus and a molar mass of 1, but some hydrogens have a molar mass of 2 because they have a proton and a neutron. As well, some oxygens come in the flavor of 16 molar mass, or AMUs. Some are 17, although 18 is kind of the second most common variation of that. So in any event, what happens in every mass spec is you're going to end up with what's called the M+1 peak. An M+1 peak, and it's just a little blip here in this particular spectra. If I stretch it a little bit, you might be able to appreciate it. There's 60, and at 61, you'll see that little teeny blip. That blip is common, and that blip specifically refers to the presence of carbon 13 or H2, which is called deuterium. So this right here is the isotope peak with a C13 or a deuterium, H2. At 59, this is a carbonyl fragment where the carbon breaks the carbon-hydrogen bond instead of the carbon-carbon bond. The last peak that I want to look at is that peak at 42, M over Z of 42. And what I want you to notice is that the original mass is 60. And if you have a peak at 42, that means that you need to lose 18 units of mass. Now, mechanistically, I'm not exactly sure how this happens, and I don't expect you as a student to know this either. The only two mechanistic pathways that I want you to focus on, and it's enough just to know these two, are either the take the electrons and leave pathway or the 3 half-headed arrow pathway. Those are the only two degradation pathways that I want to focus on. But it is common for alcohols. Alcohols have a tendency to do this very specific type of degradation, where, especially if the alcohol is long, what ends up happening is the carbons here out on the end of the alcohol have hydrogens associated with them. And if the alcohol is long enough, it's big enough that you can form a 5-membered ring between the oxygen of the alcohol and some hydrogen somewhere else in the compound. This would be a 5-membered ring. Then the oxygen has a tendency to take this hydrogen and leave as a water. The molar mass of water is 18. There's an oxygen and there's 2 hydrogens, so H2O has a molar mass of water. And again, mechanistically, I don't want you to worry about the details of this particular one. We're just going to focus on 2 different mechanisms, other than to note that if you have alcohols and the alcohol can somehow reach around and grab a hydrogen and form a 5 or a 6-membered ring, then in a mass spec degradation experiment like this, you typically see something fall off, a water molecule fall off. So we're just going to describe this right here as loss of water, which has a mass of 18, and this is common for alcohols attached to long alkyl groups. And the alkyl group doesn't have to be that long. You in ethanol can't do this because ethanol simply can't, the back carbon can't give its hydrogen over to the alcohol because it's not long enough to form that 5-membered ring. But this is common when you have a longer alcohol like 1-propanol, which is a fairly long alcohol compared to ethanol, I suppose. So mechanistically, we can explain the 60, the 43, the 59, the 31. Theoretically, you should be able to explain the 61 as just being the isotope peak, and the 42 as being something that occasionally alcohols will do, where they'll just lose a water which has a mass of 18. And so if you subtract 18 from 60, that's how we got that 42 right there. The last thing we need to do for this particular mass spec question is to look at these peaks right here. So the first thing we want to think about is the base peak. Okay? And this is easy. The base peak is the tallest peak in the spectrum. So generically speaking, it's whichever peak happens to be the tallest. And for this particular molecule, the base peak was this peak at 31. M over Z is the mass to charge ratio, which in all examples we're going to see in this particular course is just simply the molar mass of the ion. The molecular ion peak is the peak representing the ionized whole molecule. And then finally, relative intensity is the y-axis, and that represents the height of any particular peak relative to the base peak. And this is nice because it gives us an indication of probabilities of degradation pathways. And so the higher the relative intensity, the more probable that particular degradation pathway. And that's important when you're considering the stability of these ions as they fall apart. We'll make these in bold so it looks official. And I think we're ready to move on to the next question. The next compound that we're going to look at is 1-chloroethylbenzene. And the first thing we'll do is show the formation of the molecular ion peak. And this is the standard kind of way that we indicate the formation of molecular ion peaks, as 1 electron is added and 2 electrons leave. The molecular ion peak is most likely to put the cation and the radical on any heteroatoms that are present. So a nitrogen or an oxygen or a halogen with a lone pair, that's most likely where you're going to see the positive charge show up. This particular compound, though, has a chlorine, and chlorine is kind of weird. The molar mass of chlorine is 35.5 grams per mole, or 35, it's about that. I think I've rounded it off to the 10th place. And what that shows us is that the average mass is halfway between 35 and 36. And that's because the two most common isotopes of chlorine are chlorine-35, which has a molar mass of approximately 35, and chlorine-37, which has a molar mass of approximately 37. And if you have a weighted average of chlorine-35s and chlorine-37s that give you an average mass of 35.5, that means that in our solar system, about 75% of the chlorine is chlorine-35, and about 25% of the chlorine is chlorine-37. And this difference of 2, where one isotope is 2 units different from the other isotope, was not what we saw with hydrogen and carbon. Hydrogen and carbon also have isotopes, but they only differ by 1 unit of mass. And that accounted for what we call the M+1 peak in the example of 1-propanol. In chlorine, and bromine is the other atom where this is a problem, they produce a significant M+2 peak. And that's actually kind of helpful, because if only chlorine and bromine are the atoms that produce an M+2 peak that you'll see in this particular course, that means if you happen to see an M+2 peak, then that indicates with a high probability that your compound contains a chlorine or a bromine in it. Here's the spectrum for this 1-chloroethylbenzene. And there's the scale of the M over Z ratios on the bottom. So 125, 30, 135, 140. There's the molecular ion peak at 140, and there's the M+1 peak at 141. That's due to some small amount of carbon-13 isotopes or deuterium, but more important is this significant peak at M+2. That's because about 75% of the molecular ions that make it through to the detector contain chlorine-35 and have an overall mass of 140. 25% of those molecular ions that make it through the detector have a chlorine-37 and therefore produce this peak at 142. So the presence of this M+2 peak is strong indication that you have either a chlorine or a bromine. The ratio of sizes is what allows you to tell the difference between chlorine and bromine. For chlorine, the M peak is about 3 times taller than the M+2 peak. 75% is 3 times 25%. For bromine, the M and the M+2 peak are approximately the same size. The M is a little bit higher, but it's close enough to just say that they're the same height. So if I saw an M+2 peak, I'd be like, wow, that's good indication of a chlorine or a bromine. And then I look to see the comparative sizes. If the M+2 is 1/3 as tall, then it's a chlorine. If the M+2 peak is approximately the same size, then it's a bromine. So now we should be able to explain some of the peaks that we're seeing in this spectrum. And so far, the only peaks that we've been able to explain are the peaks at 140 and 142. These represent the molecular ion peaks, and both of them show up because chlorine has 2 different isotopes, and those isotopes are 2 mass units apart from each other. The next thing we'll do is explain this peak at 105. So if we go back to ChemDraw, here is the mechanism that we commonly see when a heteroatom is a cation radical in a mass spec. The chlorine will simply take its electrons and fall off. In doing so, the resulting chlorine, oops, just accidentally zipped that one off of there. This chlorine atom right here is no longer going to be picked up by the detector. The detector only identifies the compounds that have a net positive charge. And if our starting material weighed 140 units of mass and it loses a 35 AMU chlorine, then the resulting fragment will weigh 105. Or if instead you had the heavier isotope of chlorine, it would weigh more, but it would lose more and still weigh 105. So this resulting fragment is the fragment at 105 mass units. And this is the base peak, meaning that it is the most stable fragmentation that you're going to get out of mass spec. And the reason for that is because of the benzylic resonance of this carbocation. This carbocation is at the benzylic position and therefore can resonance delocalize to the ortho, para, and other ortho position. So instead of having a full carbocation on a single atom, it's a fourth of a carbocation delocalized across 4 different atoms. The other degradation pathway, that 3 half-headed arrow pathway, involves one of the electrons from the chlorine dropping down to make a pi bond. The carbon is going to match that donation with a donation of its own. So I'm going to get rid of this arrow right here. This chlorine is dropping one of its electrons down to make a pi bond. The carbon can disconnect either the entire benzene ring or the methyl group. And we're just going to focus on this methyl group for this particular question. It will take one of the electrons away from the bond that used to connect it out here with this methyl group, and then just kind of cut the methyl group free, giving it this other electron as sort of a going away present. So the product of this particular decomposition pathway is going to look like this. Let me get rid of some of the other notes that I've got here that hopefully you've written down. Okay, so now instead of having a positive, well, the chlorine will still have a positive charge, but instead of being a radical, it's going to take that lone electron and donate it down to the carbon, and then it will clip off that methyl group right there. And we're going to end up with a CH3 group that breaks off. The CH3 is going to break off as a radical and will not interact with the detector because it doesn't carry the required positive charge. This kind of floats away and we don't care so much about it. This methyl group right here weighs 15. A carbon weighs 12, and each hydrogen weighs 1. So if we take the 140 and we subtract 15 from it, that means we're going to get something at 125. But if we started off with the 142 because of the carbon 37 isotope and subtract 15, then it'll be 127. We still have the chlorine on there. The chlorine 35 and chlorine 37 isotopes are going to cause, they're still going to be there, so we're still going to see that same M/M+2 ratio, which is exactly what's going on right here inside of my mass spec. There's a peak at 125 and then another peak at 127 that is approximately 1/3 as tall. And so that's what we get in this one right here. And that explains the 125, 127. This last grouping right here is not one that we're going to show mechanistically because it's not one of the two mechanistic pathways that I want you to know. Instead, it is a common pattern that you see when somewhere in the molecule there is a benzene ring. What you see are a cluster of peaks in the high 70s, some things going on in the mid 60s, and some more peaks in the low 50s. And it has this pattern where it's high, small, and then medium. So high 70s, little teeny peaks in the mid 60s, medium-sized peaks in the low 50s. That is indicative of a benzene ring. And so when we try to explain this one, so we have a mechanism that will allow us to explain the 125, 127, 105, but here I need to use my words, and this is the common fragmentation pattern for a benzene ring. So let's wrap up this discussion of mass spectrometry. Mass spectrometry produces a lot of evidence. And in fact, in the laboratory, what we typically do is if you really want to know the identity of a compound, and we did this with gasoline from a variety of different gas stations in town, we just pulled gasoline samples and then we took them into the laboratory and we subjected them to mass spectrometric analysis, and we were able to produce degradation patterns. Now, we got a bunch of spectra that looked more complicated than this because some of the molecules in gasoline had molar masses upwards of 300 AMUs. And they were just a bunch of them. And there wasn't really a way for us to interpret each of those individually. And that's common in the laboratory. People take a lot of mass spec data. What they will do is actually purchase access to an online database that will do a similarity search of the spectra that you've produced in the laboratory with all of the known spectra on that particular database. Access to that database is expensive. And while we're not going to do that on exams, what I'm going to ask you guys to do is interpret specific peaks within a given mass spectra and try to figure out what does that really tell me about what's going on with the compound. You're not going to have access to the database that you would use in a real research laboratory. So the first thing that you should always look for is the molecular ion peak. And this is usually the tallest peak furthest to the right. And it corresponds to the molar mass of the analyte. Sometimes they'll just do you a favor and just label it. They label it with a capital M, and they'll just see a little M, a capital M, and then they'll point an arrow to which of the peaks is the molecular ion peak. But it is generally the tallest peak that you encounter over here on the far right-hand side. This is the M+1, the M+2. And then over here, kind of the same deal that it's, well, there's actually an M-1 peak that we talked about at 59 because of the loss of the hydrogen. So if I were giving this to you on an exam, I would definitely label that this right here is the molecular ion peak. But it's generally that peak that's furthest out to the right, and it tells you what your particular compound is. What else do we know from here? M+2 peaks right here. This indicates the presence of either a bromine or a chlorine. And the chlorine has a 3-to-1 height ratio, meaning that the M peak is 3 times taller than the M+2 peak, and bromine has a 1-to-1 height ratio, meaning that the M peak and the M+2 peak are approximately the same size. M-15 peaks, we did look at one of those, I'll show you that in a second, and M-29 peaks typically denote the loss of a methyl group or an ethyl group. And the ethyl group weighs 29 and the methyl group weighs 15. Oops, keep hitting the wrong button. So let's look at the M-15 peak that we saw right here. This is the molecular ion peak at 140, and you'll notice that there's a peak 15 units lower than that at 125. And so without knowing any detail about the structure of the compound, the fact that you have a molecular ion peak and then something 15 units below it would suggest that somewhere in your molecule is a methyl group that is kind of loaded up and ready to fall off. So that's pretty, and you'll see ethyl groups do the same type of thing where you'll see your compound and then 29 units below that will be the next peak. So those M-15 and M-29s are useful when you identify them. M over Z of 91 indicates the benzylic cation. We saw a slightly modified version of a benzylic cation. That was this one right here. It was a benzylic cation would be if you clipped this and just had this CH2 group right here. But if you see a massive peak at 91, then you know that somewhere in your molecule is a benzylic group. And then finally, if you see peaks in the high 70s and the mid 60s and the low 50s, that indicates a high probability of a benzene ring. Unlike mass spectrometry, both UV-VIS spectroscopy and IR spectroscopy involve a design where you have a photon source. So if it's UV-VIS spectroscopy, it'd be a source of UV-VIS photons, or if it's IR spectroscopy, it would be a source of IR photons, and those photons are fired by some type of flashlight, essentially, at a chemical sample. If the photons are ultraviolet or visible light, then the chemical sample will absorb those photons into the conjugated pi system. So you can imagine these photons making the journey through the chemical sample, and if some of them are of exactly the right wavelength to cause a HOMO to LUMO pi to pi star transition, then they will be consumed by the chemical sample as it's energized, and then the chemical sample will eject them, but in random directions. So instead of continuing to move on to the detector, which we have over here on the right-hand side, the chemical sample would redirect those photons away from the detector. So this would be the detector right here. And so again, you've got your photons, and if these photons are of different wavelength, then as they go through the chemical sample, some of them will pass directly through the chemical sample and make it all the way to the detector, but some of them will interact with the chemical sample and then be re-released, but in a random direction, and never make it to the detector. And therefore, the spectra that we produce out of both UV-VIS and IR light spectrophotometers is essentially a spectrum that shows what's missing, which photons did not make it through to the detector because they were absorbed. So let's say that maybe these ones will make it, oops, copy and paste those. So those right there will make it through to the detector. And again, these photons, so IR uses IR photons, IR spectroscopy uses IR photons, and then UV-VIS spectroscopy uses UV-VIS photons. You might say, well, that seems kind of obvious. Why would you say that? Because there is a third type of spectroscopy that we're going to talk about later, referred to as nuclear magnetic resonance imaging, NMR, or in the medical field, MRI, and that uses radio wave photons. So these are the three different types of photons that we typically use. IR spectroscopy uses IR photons, and IR photons cause vibrations within the molecule. Bending, stretching, those are the typical types of vibrations we see. And then UV-VIS photons excite HOMO to LUMO transitions is what they're referred to as. And then finally, NMR uses radio waves, and this isn't part of today's lesson, but while we're here, let's talk about this. The radio waves cause the spin state of the nucleus to flip or invert. Right? Just kind of store that in the back of your mind, information for another day. But this is kind of a summary of what's going on when we look at both all the different types of spectroscopy. If you have some type of photon source, those photons are fired at your chemical sample. The sample will absorb some of those photons, but the rest make it through to the detector. And so all the spectra that we're going to look at involve essentially what's missing, which photons were clipped out of the spectrum, and what does that tell us about the molecule? UVVIS spectroscopy is based on the interaction of UVVIS photons with a conjugated pi system. And we learned the Feser-Woodward rules and should be able to come up with lambda calc for a variety of different dienes, trienes, tetraenes, etc. So here's two different examples. We have 1 vinyl cyclohexene and 3 methylene cyclohexene, as well as my explanation for the lambda calcs that we see with either of those. With 1 vinyl cyclohexene, this is a free diene. This bond right here is free to undergo a rotation. And so the base value will be 217 nanometers, and there are 2 alkyl groups coming off of the conjugated system, so that would add 10 more nanometers to give us a final value for our expected lambda calc of 227. 3-methylene cyclohexene is not a free diene, it is a S-cis diene. These bonds cannot rotate because of the ring structure, so we start off with 214 as the base value. There are 2 alkyl groups coming off of it and an exocyclic double bond right there. So the final value is 229 nanometers. This actually would be a difficult pair to distinguish in the laboratory because while their lambda calc values are different, remember that the actual lambda observed value is plus or minus 4. So the margin of error of these overlap in such a way that I wouldn't have any confidence that I would be able to distinguish these two using UVVIS spec analysis. The first part of this question asks you to recalculate the wave number values from IR spectroscopy in nanometers. And the purpose of this question is to compare the wavelengths of IR spectroscopy with UVVIS spectroscopy. So the nice part about UVVIS spectroscopy is that the wavelength is reported directly. It's in nanometers. So most UVVIS experiments are going to occur somewhere between 200 nanometers, and I think the highest I've seen is about 800 nanometers. So if that's the photon that you're using, you know that you're looking at conjugated pi systems. Unfortunately, IR spectroscopy is not reported in units that are sensical. It's traditionally, they've done it in wave numbers, which are just kind of odd. And what they did is they took the wavelength and then they just inverted it. Well, first they put it in centimeters, then they inverted it, which I think is really odd. So the units that are typically reported in an IR spectrum, so let me show you some of the sample problems you'll be looking at in the homework. Here is the x-axis. And you'll notice that in the bottom right here in the x-axis, if you can read that, it says wave number, and the units are centimeters to the -1. And I think I might have cropped that off of there. But notice how it starts off here around 500 wave numbers. Here 600 is generally where people start taking the spectrum seriously. And then 4,000 wave numbers is where they stop taking the spectrum seriously. So this is the standard range of IR spectroscopy. And within this range, though, wave numbers are a weird mathematical manipulation of wavelength. So when you say something has a photon has a wave number of 600, what you're really saying is that the wavelength is 1 over 600 centimeters. Right? So a wave number of 600 inverse centimeters is equal to a wave number of 1 over 600 centimeters. So I'm going to actually set that up as 1 over 600 centimeters. So that's the decimal value right there, 0.001667 centimeters. And if something has a wave number of 4,000 inverse centimeters, then that means that the actual wavelength is equal to 1 over 4,000 centimeters. We can now convert from centimeters into nanometers. And I don't know the conversion off the top of my head between the two, but I do know that 100 centimeters is equal to 1 meter. and 1 meter is equal to 10 to the 9th, so 1e9 nanometers. And therefore, if 100 centimeters is equal to 1 meter, and 1 meter is equal to 1 times 10 to the 9th nanometers, then 100 centimeters is equal to 1 times 10 to the 9th nanometers. So I can take this numerical value right there, and if I multiply it by this 10 to the 9th nanometers and divide it by the 100 centimeters, then centimeters should cancel out, and that will leave me with units of nanometers. So this right here is the upper end, the longer ones, the longest possible nanometer length. And we can do the same mathematical operation. I'm simply just converting this value in centimeters into nanometers using dimensional analysis, as you would have seen in general chemistry. So we multiply it by the nanometer conversion and divide it by the centimeter conversion. All right, so those are the two values, 1.67 times 10 to the 4th nanometers and 2.50 times 10 to the 3rd nanometers. If I don't want these in units of exponential notation anymore, you can just format this to show it as general. There we go. So while the range of UVVIS spectroscopy is from 200 to 800 nanometers, the range of IR spectroscopy is from 2,500 nanometers to 16,666.6666 nanometers. So just to help you appreciate, the photons that we use in IR spectroscopy are much longer than the photons that we use in UVVIS spectroscopy. So, and if the wavelength of these photons is longer, then that would suggest that their energy is lower. So IR spectroscopy uses lower energy photons. This is equal to the, what was that? That was the 600 wave numbers. And then the other one was the 4,000 wave numbers. Okay. So what is the homework going to look like for this one? Well, we do have the required textbook problems, and I'm going to step away from chalkboard problems and instead ask you to work these as homework problems and submit the correct answers with your homework assignment. And then at the beginning of the next lesson, what I will do is start by going over the answers to these homework problems. But I really need you to try to beat your head against these particular homework problems instead of just watching me give you the answers, so that when the exam comes, that's not the first time that you've had to struggle with how to organize all of this information that I've given you today. So question number 1 is going to give you a variety of different mass spectra, and you need to identify the compound that matches these various mass spectra. And I've just given you the names of these compounds. These all involve functional groups that you don't necessarily know how to name. So for example, pyridine is not really something that we've discussed the nomenclature of, so you probably do need to Google some of these names in order to come up with the right structures. But so the first question asks you to just kind of match the mass spectra to the compound, and then the second question asks you to match each of these compounds to one of the IR spectra. And you are definitely going to need to consult this table if you haven't memorized it already, so that you can figure out how to match these different compounds up with their appropriate IR spectra. Do your best to try to come up with these, and then again at the beginning of the next recorded lesson that I'll post for you guys, I will start off by going through all of these homework problems before I introduce new material to you.